All right, we're on. We're live. How's it going, folks? How is it going? I hope everyone's doing great. Let's see. I'm putting things in the right place. Putting things in their place. We're just about to get rolling. Today we're going to hack on jank. What do you know? Who would have guessed? Who would have thought? It's true. We had just had a blog post go out. Hope you guys all checked that out because that was a big one. There's a lot going on in that one. Welcome, welcome. Welcome, welcome. And turn down my jams. So we're gonna work on optimizing jank today. Who would have guessed? I know that's been the theme. It's gonna continue being the theme. But we're optimizing different stuff this time because we finished up our Fibonacci optimizations. We're gonna be jumping into optimizing a ray tracer in jank. We have where is that? I must have something here, right? I know I have something here. Probably this guy. Can I just open this with Chromium in here? Firefox does this. Okay, nice. Chromium does this too. Whoops. So this is what we're rendering. Although we're going to be rendering a smaller version of this. And our goal is to optimize this just like we did with the Fibonacci. Our goal is to optimize this to be faster than Clojure. And just like Fibonacci, to start with, we're not faster than Clojure. But just like Fibonacci, I think we're going to get there. So one of the things I was working on was, this is going to take the, okay, I need you to go to the background, buddy. Can't believe you don't fork. Can't believe you, Chromium. Oh, and then it's going to be outputting things here as well. No, we're not doing that. We're not doing that. I will not tolerate this. We'll open via D menu. And then I thought that I just, wait, home J. Yeah, that one. Okay, now we're clear over here. So one thing I was just working on here is I have optimized the, what's this? Highlighter, language tree sitter stuff, decorator conceal line. And then that breaks tree sitter highlighting after that? Maybe? It does. Tree sitters being such a pain in the ass recently. What if I disable conceal? Because that was complaining about conceal. Where's conceal? This looks like what I want, but what's this? Looks like I'm setting it in two different places. We're going to disable both of those. So that was Q2. Still, okay, but now it's not, huh. Maybe what I want is to just disable tree sitter for Vim. You know, maybe we should just solve all my editor woes this stream instead. Wouldn't that be lovely? Oh, hey, Robin, how's it going? Where is tree sitter markdown? Yeah, we're just gonna disable this. Donal, how you doing? I'm great, Robin. I'm doing really well today. What a time to be alive. Enjoying life. This still, so now we run into, okay, why am I running into issues with conceal line for markdown when I have specifically not enabled markdown? Like here, markdown is not enabled. This is ensure installed. Wait, I had a previous hack here that disabled if lang is markdown. That's interesting. Hey, Nick. Welcome to the stream. What is dot? What are you saying? What are you trying to convey to us? Yeah, and then more, so it still get conceal stuff. I wonder, so this should disable highlighting if lang is markdown. And then this also disables it if it's, I guess there should probably be a return false here. But it doesn't seem to be disabled. I'm going to go back in, and then I'm also going to disable these one more time. Oh, I did Q1. And now we get another. I too quickly went through that error. What was this one? Okay, so more tree sitter, but now a different thing, calling range on a nil value, blah, blah, blah. Huh. 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 Yeah, I wonder if there's a better way to disable tree sitter entirely. Let's search. Tree sitter disable. Well, let's just say disable markdown. Maybe we'll find something there. If not, then no syntax highlighting of tree sitter, blah, blah, blah. Don't conceal, blah, blah, blah. Lazy tree sitter, blah, blah, blah. Okay, so we're just going to go here. Wait, this is archived? Why? Why is this archived? Oh, is this because tree sitter went into NeoVim? Like that's. See, okay, here's the thing. If you're gonna archive a fucking repo, say why. You know, update the README before you archive, and you say, this is no longer maintained, use this fork, or something like that, right? Like, for example, I know that Control P does this. If you go to the original Control P, which is just a Vim plugin, then actually it's not even archived, but it says, hey, this project's unmaintained, you should use this fork instead, right? Or if you go to like one of my guys, ncurse's wrapper for Rust, it's archived, and then there's it's been archived. This is the last release. Use this other stuff instead, right? What is this? This is a rewrite, specify master branch. I don't even know. I don't even know. There's nothing here. But I do believe that this was upstreamed into NeoVim, which is why. But when I search, so I guess I'll just have to search NeoVim GitHub. But because I'm not logged in on Chromium, I'm not even going to be able to search this repo. So we do have tree sitter default highlighting for Markdown. Seems like this is actually a one-line change, and then whoever changed this also just ended up doing a whole bunch of fucking highlighting changes in here. But this seems like the actual functional change based on the commit message. It's the very last file. So we do a tree sitter start inside of markdown.lua. And so are they just, is that like hard coded? Does that not factor in that I have disabled this? I don't know. Hey Matt, you nerd sniped me last week, but I got fib down to ever so slightly faster than Clojure JVM. Fuck yeah, you did. Nice job, my man. That feels good, right? Feels great. Yeah, absolutely. What are we doing today? Well, I was gonna do some hacking on the Jank compiler, and then I started getting some tree sitter errors in NeoVim, and then I spent 10 minutes looking into that until you until you jumped in. So I don't know. Maybe we're gonna just move on to this. Seems like whenever I open a markdown file, tree sitter just dies. And then if I open up any other file, oh wait, this is fine. Wait, hold on, let me just, so I open up this, we have highlighting. And then I open up this, then we get an error. And then I go back to here. Oh, no, we're good. Oh, we're good. Okay, so this just affects the markdown file. That wasn't the case before. I think the other stuff I disabled, made it so that it's not affecting other files. Fine. Yeah. I know I complained about this in a previous stream. I don't want to repeat myself too much, but I'm pretty sick of like, I haven't changed my NeoVim config in, I don't know, several months, but now things are broken. Thinking I'll just probably go back to Vim and then get rid of all of this fancy telescope noise and and other stuff. I like Tree Sitter. Like in general, I think it's a great like way of especially highlighting that is far more semantically accurate than regular expressions, which is how highlighting's been done for decades. But hopefully I can still use that in normal Vim, but all of this shit, 90 lines of fucking Lua to just get some syntax highlighting. Like if I have to use regex, then I will. Yup. And also like I had to specifically hack this in because I found that if I open up NeoVim with Tree Sitter for files that are like too large, then it just like it's completely unusable. It just completely locks up. I can't even move up and down. Like it just takes like minutes to process each input, and it's because of the highlighting. So yeah, things like this is the sort of thing that never used to be a problem with them. You know, it was just like, if it was slow in any way, it was your fault. And now it's slow in a lot of ways. And for sure, some of it's my fault because I'm choosing to use this stuff. But also, I think it's the ecosystem's fault, the community's fault for like going down this path. That's all I'm going to rant about for that. We're moving on. Well, I'm going to bring this guy back into here. Johnny, I don't know if I said hi already, but hi. Hope you're doing great, Johnny. Yeah. So what are we doing today? Well, I was working on, the next benchmark. And what is the next benchmark? We're going to see as soon as I close this tab. Hold on, the next benchmark is a ray tracer. And there's already a ray tracer that I've written in Clojure. It works in Clojure JVM, and it works in Jank. And we're going to be optimizing this. So like Fibonacci, we're going to try to beat Clojure's speed. And also, like Fibonacci, we are starting out slower than Clojure. So there is work that we need to do. Wasn't around last time. What numbers did you get on Fibonacci? So Robin, there is a whole blog post that went out about all of the work that went into Fibonacci. And the latest blog post on the Jank blog, but I'll summarize the numbers for you. We started, I even got little fucking graphs here. I really don't like these chromium scroll bars. Like, ooh, that's ugly. But this is what we started at. Big 5.5 seconds compared to Clojure's 200 milliseconds. And we made it all the way down to, what is this, 114 milliseconds. So Clojure was at 200. We made it down to 114. And so not quite twice as fast as Clojure, but almost twice as fast. Also, yeah, we do have that RSS support. Actually, I wrote the RSS that's XML, I think. I wrote that myself, if you believe that or not. I think we have janklang.org, and then in here we have like a feed. Fuck, what's that called? Feed. Blog feed. Feed. RSS. Fuck, where is this even? I don't even know. Man, I did such a cool thing, and then I like can't even find the code to show it. Yeah, I don't know. I don't remember where. Source COJ. Yeah. Well, oh well. Anyway, moving on. Johnny, you're trying to install Jank and you're running into an issue. Dependencies, but it's not available. Yeah, you need to. It depends what version you're based on. So Jank is compatible with. If we go to installation, I think, markdown, right? So we have here 2404, 2410, 2504. If you're outside of this, then they're going to be binary incompatibilities, package incompatibilities, everything like that. Because that's the way the native world works. So yeah, we can't just like have a binary that you build for 2404 and have it work on what's the new one, 2604. Doesn't work. So we're gonna need to either have like multiple binaries built, or we're gonna need to like make them more portable by static linking more. I don't know. But yeah, you got to make sure that you're operating within the realms of what is supported. Why can't Clojure backward compatibility be a standard? Yeah, I mean, like I would love that as well. I'm gonna try to make that the case with Jank, but the entire the entire native ecosystem is fighting us on that one. Yes, sirree. Okay. So I was explaining, hold on. I was explaining, so we did really well on the fib and we beat Clojure like handily, and as did Matt. So pats on the back for both of us. The next stop is this ray tracer. Now, the ray tracer, I don't have the starting numbers here. It was something like 49. Clojure is at like 22, let's say. It's 21, 22, 23. Clojure is at like 22, and we were at like 49. And I switched to NAND boxing, so that way we can do inline floating point values as well as inline integer values, to completely avoid GC allocations for all floating point values. And this drops us from like 49 to like 30, 34. So that's a big jump. And then I was just today/yesterday, I was working on taking the inlining work that we did for Clojure Core. And so we had done a bunch of like inline stuff, so that we could inline calls to vars for the arithmetic for fib, but we didn't extend that to like all of the other usual suspects in Clojure Core. And so I did that. And then I found, so I haven't yet been able to get the final numbers to see what the effect of that was, because I started running into some other issues once I started inlining all these things. A couple of issues. One was an analysis issue which I fixed this morning. And another one, which is what I was going to start by looking into on the stream today, is a compile time performance issue, where all I did was I added inline to, I don't know, let's see, let's just do a search. So we can see in the bottom here, 85 results for inline in this file. So I added inline to a bunch of ours, and that was just because, like, might as well, right? It's Clojure Core uses direct linking anyway, so we don't ever expect to be able to redefine these things, and all of the like basically all the functions that just end up doing some interop, things like this to check if it's nil. Actually, we have an even better way of doing this. We should just check dot is nil on this. Yeah, this is even simpler. But anyway, other things like count, is just boils down to a C++ call for sequence length. So like there's so many of these, turns out there are about 85 of them that just do some interop. And so I added inline to each of these. But then I noticed that the compile time for Clojure core just exploded. It just fucking exploded. And I don't know why. It shouldn't. It shouldn't have exploded. And so we're gonna do some investigation, and I'm finally getting through more of this soda as well. It's been like, I've been getting through this soda, I swear, for like 3 months. So I made a small reproduction case, and I want to show it to you. So we have temp meta, and we have temp meta, no meta. So here's what I've done. I've taken about 100 lines from the start of Clojure core, and these are just like all the all of the functions that we end up defining in Clojure core. Basically, all of these are just implemented via interop, as we can see. Like so, and you notice that you might say like, oh, why are you using def and fn star to define these functions? And the big brain answer is because we haven't defined defn yet, right? So like early Clojure core really is trimmed down, and we use fn star because fn star is the actual special form, and fn is a macro that does destructuring and then generates an fn star. Now the Clojure docs will tell you that fn is a special form, but in terms of the way that the compiler is actually implemented in Clojure, as well as in Jank, the actual special form, the one that's baked into the compiler, is fn star. Same as let star, and loop star, and so on. And then the rest are just macros. So this is 100 lines of just defining some initial functions. Now this is the no meta version. Now I have the same exact thing, but it's actually, here we have all of the metadata for arg lists, doc, and inline for most of these. Now, some of them don't actually have inline, like we can't inline, actually we could inline this one, but we don't do inlining on like F first, where is that? But yeah, because F first is just calling first and then calling first again. So like if first has inline, then F first is just gonna be, like both of these calls are going to be inlined. There's no point having inline docs on this. But this is just all the same stuff, except we have some metadata. And these also have private metadata. Okay, so looking at these two, what I've done is I will say jank compile module, module path. These are both in a temp directory. And then there's no meta, and let me do this. Okay, so we see here that this took about half a second, right? About 500 milliseconds. And now we'll compile the meta version. So it's the same exact thing with just with metadata. 3 times longer. This is 1.5 seconds. So So this is just 100 lines, right? This is just 100 lines here. And it ends up taking an extra second. Now, like proper Clojure core is like 7,500 lines or something. It's a lot of lines, right? And so all of that metadata that we have ends up, I don't know if it's linear yet, like maybe it's just 3 times longer across the board, or maybe this ends up being like some sort of exponential thing. I don't know what the problem is. But when I added that metadata into Clojure core, all of a sudden, like it was no longer practical to compile Clojure core, like within my lifetime. I let it run for, I don't know, half an hour this morning. And as I was just working on other stuff, and then I was like, okay, yeah, like if it's not going to finish in this time, then it's not going to finish. And so I just killed it and instead switched to a much smaller example so that we can actually, compare this. And so this is the first thing I just wanted to see if we could get a glimpse into what was going on here. Now here's the crazy thing. Let's take a look at the generated code, because that's going to be the first thing that comes to my mind is like, all right, well, is there like a huge amount of code difference between these? And so if we do a Jenk print code gen, this is going to be the fully formatted C++ code that we end up generating. And so we have this no meta namespace, and then just a reminder. So basically we have here 100 lines of just a bunch of functions. And these functions will use some constants. I guess we don't really have that many constants here, do we? We probably have nil implied. And then I guess we'll have an empty list here. But most of the things that are going to be lifted are going to be vars. So we do have constants here. I don't know what all those are. This is probably our empty list. And then we have a bunch of lifted vars. And these all just end up being globals in this top level no meta namespace. And then we have all of our functions. And so if we take a look at something like empty, right? Empty takes an O and then calls Jenk runtime is empty on it and then returns the result. And so let's take a look here. It takes an O. Of course, it takes its implicit this parameter as well. So it takes an O, calls Jenk runtime is empty on it, converts that into an object and returns it. So this is the C++ equivalent of this function. And it can't really get much thinner than that. So these don't change. These don't change between no meta and meta because there's nothing here that has to do with metadata. So what does change? None of these functions will change. And then we have this, we have our entry point for this whole module that we're compiling. And so there's always this, so if you're compiling a module called foo, and modules in Jenk are basically just namespaces. If you're compiling a module called foo, then you're going to end up with this jenk_load_foo function. And this is kind of our well-known entry point into that module. This is what we call in order to initialize that module after we've loaded the object file for that module. And it's going to create the namespace. It's going to set some internal stuff. It's going to register our globals with the garbage collector. It's going to initialize all of our globals. And then you'll see here, we end up initializing all of our metadata. And so our metadata here is represented as these maps. And we read those in using Jenk read, and those get read in from a string. So these actually get lexed and parsed basically at startup time. And the reason that we do this is we could generate some C++ code that creates a map and interns this keyword and then creates another map and interns this keyword and then interns this string and then creates and like interns this keyword and then interns this string. But the C++ code that would be necessary in order to represent this data as code would just be enormous. This would be like 10 times more code. And it would be like a lot of template instantiations and everything like that, because that's just how those objects are created. And so in terms of code generation, both in terms of size as well as in terms of performance, it just makes sense to render out the string instead and then just lex it and parse it at real time, at runtime. Not defining empty question mark as not seek in Clojure is pure evil. I don't like that seek. I've never bought into that seek idiom. I think Rich's argument for that is weak, and and that there's no clear win because it's a purely subjective thing. There's nothing wrong with getting a value and then doing a not. Whereas, and like that is a perfectly clear approach that basically any programmer is going to be able to read that code. Like, is it empty? Is it not empty? Like, that's just super fucking obvious. I write code to try to be clear to myself in the future as well as to other people, and using the seek idiom is not clear. I think it's a terrible idea. That's an aside. So we have all of this metadata. Now here's the crazy thing for those of you who are actually following as I work through this, because I don't know the answer here. I'm just bringing you along with me as we figure it out. We're compiling the no meta version here, right? That's what we compiled. We compiled the no meta version, which is to say we have all of this stuff without any metadata defined. But all of this stuff here is metadata. Like, this is the metadata for, let's see, line 37, column 6. What's on line 37, column 6? Well, that's F first, right? So this is the metadata for F first. Let's take a look at here, line 29, column 6. So line 29, that's fresh seek. So like, we actually have all this metadata, and that's because vars by default have metadata. And that metadata is the source information for the var. And so it's not that we, like, although I called this no meta, all it's actually saying is we don't have any like custom meta that's being specified. But every single one of these vars already has meta still. And so when it comes to code gen, adding a little more meta should just mean having these strings be a little longer. That's it. That's it. So why is that taking 3 times longer? And it's probably because my assumption here is not quite right. So what I want to do, Johnny, you said, do you think meta reading at runtime will stay like that forever? Or are you planning on changing it? I think it's probably going to stay like that for the foreseeable future. I don't see, I mean, unless somebody comes up with a brilliant idea for how to make it different, like encoding data in C++ code is never going to be a better idea. It's just not. But if it ever becomes a problem, it would only be because the lexing and parsing of that data becomes a performance concern. Now, right now, compared to everything else that we need to do at startup, it's never even registered as like, oh, this is a problem. And that's just because like starting up the Clang JIT runtime giving it our precompiled header file so that it knows how to deal with the whole C++ side of Jank, the whole C++ API of Jank. Like that takes 300 milliseconds on my machine. And so Jank's sort of baseline startup is 300 milliseconds. Now that's the sort of thing where like, yeah, I mean, if we can trim down that precompiled header, then we can hopefully get that down to like 100 milliseconds or something like that. Whereas the parsing of the meta is like, I don't know, less than 10 milliseconds. It's nothing. I would say it's probably less than 5 milliseconds. It just doesn't even show up when I look for these things. So if we get to a point where it starts showing up when we start profiling the startup time for Jank and Jank compiled programs, then the solution is going to be most likely to just optimize the lexer and parser rather than to change how we represent metadata. Okay, so here's what I wanted to do. I want to do all of this, but I want to save all of this. So let's do a no meta.cpp. And so we should have a no meta.cpp here that has all this in there. Good, we do. Now I want to do the same thing, and I want to just compile meta, and I want to save that. Good. Now let's compare. Okay. So if I open up, we'll do no meta and we'll do meta. And I'm actually going to do a, so this is no meta and this is meta. And that's not what I want. Now, what's the size difference? So one is about twice as long. The meta version is about twice as long. Okay, now the question is, so the first question is, wait. Why do we not have a namespace meta at the top? Wait, there's a difference here. What was the difference? Wait. So if we compile no meta, we're doing print codegen phase 1 compile module path no meta. And if we do the same exact thing, I'm just not even going to use the other command. I'm just going to modify this command. We do the same exact thing here for meta. We end up fascinating. Oh, I think we're on to something. So, do we have a vimdiff? No. So here's the thing. When we do the meta side, we end up compiling each of these functions. We end up JIT compiling each of these functions. And then we have our namespace. And that's 600 lines. So if we were to delete everything above this, then we'd be at 550 and 565. So it's actually basically no longer. It's basically the same between the two in terms of the generated AOT compiled code. But we have all of this additional JIT compiled code showing up here before. Now I could reproduce that if I take the no meta version and I force eagerness with eagerness eager, which I still haven't changed to just being an eager flag. Now we're going to see, so now we're going to see in the no meta version, we're going to see a whole bunch of JIT compiled functions first. And then we're going to, after all of these, then we're going to see our namespace. So here's the thing. This is the difference. And also, we're going to see that that took quite a bit longer. So let me compare one more time. So if we take, let's do the no meta version. So that's half of a second for the no meta, or at least no additional meta, and lazy compilation. But if we do no meta with eager compilation, now we're up to basically a second. So we've doubled the time. So what this means is, for some reason, having the metadata here is forcing us to compile each of these functions eagerly. That's it. That's my analysis, because otherwise, when we look at no meta here, at the very top, we just have this namespace. There were no JIT compiled functions before. And if there were any functions that we JIT compiled, we would have printed them, because we are printing, this print codegen says we're going to print everything that we compile. But instead we just jump right to AOT compilation. However, when we do the meta one, same exact command, we JIT compile all of those different functions. All of these functions are JIT compiled before we get to the namespace 600 lines in. So we can deduce here that adding metadata, explicit metadata here, somehow subverts our deferred compilation. But why? Why? 2 days before my bachelor's thesis submission deadline? Are you just getting started? Is it going to be a very busy next 2 days? Or are you ready? So we do our deferred here. When we evaluate a top-level function, we check if there's a current var. And if there is, then we know the var that we're working with, and so we create a deferred function instead. Wrote about 80 pages within 1 to 2 weeks. Recommendation used to be 30 to 50. Have you ever heard the term, Johnny? There's a great phrase. I don't remember where it's from, but it's such a great phrase. It was apologies for the long letter. I didn't have time to write a short one. And that's the idea that being able to take your points, your thesis, and turn it into something that's concise rather than rambling is what takes a huge amount of time. Like getting the idea, like having the ideas and dumping them out on paper is one thing, but turning it into something that's concise and not rambly and has a good narrative and everything like that is the hard part of writing. I think that's certainly my case when my experience when it comes to like writing talks, for example. I'll write a narrative for a talk and have all these points I want to capture, and then I'll start working on slides, and then I'll have like 150 slides, and then I'll talk through the talk. I'll be like, okay, I have 20 minutes for this talk, and then I'll go through it, and I'll be like, oh, okay, that takes 45 minutes to do. And then it's time to just trim it down. Last 10% takes 90% of the time, for sure. There's that. There's the 80-20 stuff as well. But yeah, it's like, sorry for the long letter. Didn't have time to write a short one is a great phrase to keep in mind. Now, what is this? We set when we I might have to step through this because I don't understand why. I don't understand why we need to just in time evaluate these. So let's do it. Let's take this meta approach, I don't want to delete that, and step through. And then my mentees, I have multiple mentees who help me on Jank. They often ask me, how do I get better at debugging? So did you do any debugging on that stream or this stream? So I'm doing debugging here. Watch this one. So we have this eval function that we want to break in for eval for def. And I'm just going to specify that based on the line number, because they're all called eval and I want to get into a particular one. So I'm just going to say evaluate.cbp and 279. And like GDB is going to figure out the rest. I'm just going to do this. So file name, colon, and then the line I want. GDB is going to figure out like, okay, you mean this one. And you can do that same thing with like symbols if you wanted to break on a particular function name. You don't need to like fully qualify it most of the time. GDB is going to figure it out. So let's step into here, and we're going to have this, I'll just switch to this view. So we're going to have this expr, and let's see if we can, we probably can't do this, but I'm going to try. No, it's not going to let me. So instead, can we just check expr name? Yes. Can we actually get a string version of this? Yes. And so we can see here that this is Clojure core empty question mark. And that should be our first one that we're going to work on. Yeah, empty question mark. So here we go. So we're going to get our metadata for this. And meta Nice. So you'll see that the bytes here don't show anything useful, and that's because this is a large string. So we have to take a look. We have to continue, and then we'll have to take a look at the large version here, and we'll see here that we have the full string here, but it's not actually shown. So we're just going to do set print elements 0, and that's going to allow us to print everything. Because by default, GDB is just going to try to cut things short so that they don't get too long. So let's just do a set code string again, and then we'll step through that. And then here's our full string. So we can see that our meta has source information. This is the Jenk source about the current module, the file, and the start and end. And then it has arg lists, it has doc, and then it has inline. And so arg list, doc, and inline are here, and then the source information is just automatically put in there by Jenk, by the compiler, I mean. So we're gonna set, and then if the value is none, that's not the case. So now we have this value. Now the value should be a function. So we should jump into here, and we do. So we set current def var good, and then we try to evaluate the value. So this current def var is a thread local variable that keeps track of the current var that we're working on. So I'll give you a little context of what this file does that we're in. So we're inside of evaluate.cpp, and this is for evaluating the Jenk AST. And in my first Clojure Conj talk in 2023, oh man, let's pull that up. Let's pull that up. So how to build a Clojure dialect. We're not going to watch the whole thing, but I want to show that bit. Lexical analysis. Wait, where'd my things go?
Hello, everyone.
No, shush. So, right, this one. Wait, that's not where I clicked. $13.01. Man, this is...
Now for evaluation, I have to get something off my chest here. I'm sorry if this sounds like rant.
Oh, wait. I'm not outputting audio. You guys aren't going to hear this. Okay, hold on. Also, I have to stop my music. Okay. This, and then audio output. Yes.
Clojure is compiled. We all know this, right? Clojure is a compiled language. I checked Wikipedia. Clojure is a compiled language, okay? No, I checked Clojure.org. Clojure is a compiled language.
I forgot that water bottle.
Clojure compiles to JVM bytecode. We know this. Clojure is a compiled language, except for when it's not. When is it not? Actually, a lot of the time. Everything on the left here. If you were to send this to the REPL from your editor, evaluate a whole buffer, evaluate a single form, doesn't matter. It's interpreted. It's not just-in-time compiled. Now, everything on the right, function expressions, lets, loops, which are a form of let, which was surprising to me, but makes sense, and try and throw. All of those require just-in-time compilation. Now, anything inside of those, like a function expression with an if inside or God forbid, a def inside, that will still be just-in-time compiled, but everything on the left is interpreted. Now, maybe that blew your mind, but here's a pop quiz. Take a look at this code. We have a few vars, top level. We're defining add, that's a function. I'm using def and effn here, but defn would effectively end up being the same thing. There's no trickery here, I promise. And we define 5 to some function call. 5s is some map. We have a top level when. We are doing some arithmetic, we're checking some equality, and we have a print line. How much of this is actually just-in-time compiled? Well, I gave you the answer in the last slide. Only the function. Every single thing else, if you were to send this through the REPL, is not just-in-time compiled. We don't generate bytecode for it on the fly. Instead, we just do the work.
So I don't
Now,
know
why
if
is
if this is new info for all of you, but I think that most people really don't have this mental model for the way that Clojure works. And then the reason why I said like Clojure's compile is because when you look online, like early days of Clojure for the mailing list and whatnot, this is what the core team was saying. Like, no. Clojure is a compiled language. Clojure is always compiled. If you look at the early docs for Clojure, it's like, no, we always compile. And it's so, it's so wrong. Yeah. So when you take a look at also, let me quiet the output again so then I can put my music on. When you take a look at the Clojure compiler, and let's do that right now. Projects, third-party Clojure, vim compiler.java. And let's take a look at something like a def expr. So the def expr is the AST expression for def, right? And it's going to have, what do you know, an eval function on it, right? And so whenever you have a top-level def, which is basically most defs, and you're not AOT compiling, you're just evaluating, which means you're either like running a file or you're sending some code to the REPL or whatever. You're just going to analyze that def expr, and then you're going to call eval on it. And all that's going to do is we've already interned the var right here. Like when you create the def expr, we already have the var right here. So we just store that. And so if you have this init, then all we do is this init provided is just another expr. So we have our init provided, and then we have our init expr. And so we just take our init expr and we call eval on that. We have no idea what that is. That's some other expression. We're just going to go evaluate that. And so if that's just like 5, well, that's just going to eval to an object for 5, right? And so if that's a function, well, then we're going to go JIT compile that function. But if it's a function call, then we're just going to call. We're not gonna JIT compile a function call. We're just gonna call the function. And so what that's going to give us back is an object, and then we're just going to bind that as the root of the var. And then if there's meta, we're going to update the meta on the var, and then we're going to set whether or not the var is dynamic, and that's it, right? So this is interpreted. This is not JIT compiled, and the reason for this is simple. It's just if you were to JIT compile this, what would you do? Well, you would JIT compile a function that interns the var, evaluates the value, sets the var's root, and then updates the meta of the var, and then sets whether or not the var is dynamic. That's it. But you would have to pay the cost of doing code gen to JVM bytecode for that function, and then loading that function into memory as executable, and then calling that function to have it then do this work. So there's all this additional compilation costs that would be required when you have all of the data that you need, because the compiler is directly integrated into the runtime for Clojure. Just fucking grab the var and bind the root, right? And so a lot of stuff that we have can just be evaluated. Def is one of those, but like var deref, what do? You find, we're back into Jenk code now, because in my opinion, it's actually much easier to read. You find the var. This is some AST expression for var deref. You find the var, you call deref on the var. There's your eval for a var deref. A var ref, even easier. Find the var, return the var. And then calling, you actually have to like eval the source, the function thing that you're trying to call, and then you have to do parameter matching and everything like that. That gets more, but like list, build the list. Primitive literals, generally we just evaluate those directly. So anyway, this code that we're in here is eval for our AST expressions. And the way that deferred compilation works in Jenk is when you evaluate a def, we have this thread local variable called current def var. And this keeps track of the var that we're currently evaluating. And so if you have something like this, where you say def empty ? And then some function, we're going to evaluate this def. We're going to intern this var, and then we're going to store right here. We're going to say current def var is equal to var, this var that we have. This is for empty ? And then we're going to go evaluate the value. And so what is the value here? Oh, that's this fn star, right? And so what we have is a check right here. When you go to eval a function, then we check, okay, do you have a def var? Which means, are we currently evaluating a function that's going to go inside of a var? Because you could eval a function that's just like a anonymous function or a local function, something like that. It's not going to be directly tied to a var. But if it is tied to a var, and we have lazy compilation, which is our default, then rather than JIT compiling all of the C++ that's necessary for that function, we're going to generate the C++ that we need, and then we're going to create this deferred C++ function object instead. And the deferred C++ function object, it has basically all of the data that it needs to actually create the function object, but it doesn't do it until it's called. Most of the time, in the case of something like Clojure core, only about half of the Clojure core functions, it's actually, I think, a little less than half of the Clojure core functions get called during AOT compilation of Clojure core. And that's because like those half-ish that do get called are just because later functions end up using those functions. Especially macros end up using those functions. And so you actually need those as part of the runtime while you're compiling. But most of them, you're not actually going to compile. And Clojure core is kind of unique because you're building up macros and sort of building a language. But if you imagine like a game or something like that, if you're AOT compiling, you're not going to be compiling even 20% like of those functions. You're not going to be loading them into the JIT runtime. Like you'll still create these deferred CPP function objects for each of those functions, but they're not going to be called during AOT compilation because everything is called from your entry point, which is main, and main's not going to be called from your AOT compilation. It's only called when you actually run your program. So this makes AOT compilation significantly faster because we don't need to actually load all of these JIT compiled functions into the JIT runtime. The slowest thing that we do in Jenk is compile C++. Compiling Jenk code, not a big problem. Like compiling Jenk code to our IR or to our targeted like C++ code gen, not a big problem in terms of performance. We could do a lot of that. But to add that C++ into the JIT runtime, that's slow. That is the slowest thing that we do. And so this deferred C++ function allows us to avoid that the majority of the time. Now, what we found here is that this case of meta versus no meta is 3 times slower because we're not actually deferring the compilation of that C++. For some reason, this branch seemingly where we check, okay, we're evaluating a function. Do we have a current def? Are we compiling lazily? If so, let's just create this guy. This doesn't seem to be taken. Or it is taken, and then this function is being called. Because what deferred CPP function does is, if it's called, it then it has a handle on the var, and it has a handle of the C++ code that's needed. And when this deferred CPP function is called, it will JIT compile the C++ code, turn that into an actual function object, and then it will replace the root of the var with that function object. That way, any future calls that go through the var will not go through this deferred CPP function. And then it will proxy the call onto the new function object. I think one of the reasons why it doesn't need to be the code is only executed once anyway, no loop, etc. Yeah, I mean, you're talking about things like just-in-time optimization. Like if it were in a loop, then you would potentially benefit from optimizing the code. But the thing is, like, the JVM is adaptively optimizing all of the code that's already running anyway. And so in that Clojure example that we're looking at here, like, this code can also be adaptively optimized at runtime. You know, there's no point in JIT compiling some other code that does the same exact thing that could then also be adaptively optimized. There you go. Bunch of info about that I'm sure all of you wanted to know. Okay, so that is why we're stepping through this code. Now let's go back to our debugger, and we're going to step into this. And we're fine here. We can step over that. Step over that. Now we want to step into this. And then we're going to step into this. Okay, here's, I'm back to giving advice to my mentees who watch these and want to learn how to debug better. When you're stepping into things, I wanted to step into that eval function, but I ended up stepping into this static refcast. GDB has a command called finish, which you could just type by the shorthand is just fin. And fin just brings you up out of the current function. And so if you want to like step into something, but you end up stepping into something that happens before that, just jump out of this with fin, and then step back in. So we're gonna step in, and now we're in eval. And let's see. So we have eval for function. Why do we have an eval? Okay, so we have eval with a function that has a string. What is this string? We don't even use the string here. What's the point? It's the var name, but it's not even used. Huh. Okay. Could be dead code. Could be something I'm missing, but either way, we're going to step into that. Again, we ended up stepping into the creation of an immutable string from that string literal. Don't care about that, so I'm just going to do fin. And moving on. And so we stepped into this. Now, let's see what is going on here. So we get our IR module, and I'm expecting to get into here. So let's just see. Okay, we do get into here. Fascinating. So we do end up making our deferred function object. And then we reset our current def to nil. And then we return our function object. So that means that it's not being JIT compiled here. The compilation is being forced later on. Why? Why? And when? So let's jump into our deferred CPP function. And let's put a breakpoint on deferred CPP function call. Now, I'd actually want a breakpoint on every single one of these. There are a bunch of different overloads. Well, actually, there's just this one. But we end up forwarding all the others, so we only overload one. So let me put a breakpoint on that. And now let's continue. And so we're going to continue. So I'm going to disable breakpoint 1, which is this eval breakpoint. Don't care about that. And okay, so now we're in our deferred CPP function. So we just forced this. We're going to force this. Why? Let's take a look at our... I wonder, is the problem... So for inline, we're going to be calling list. So presumably list is going, like, assuming any of these are inlined. I guess first will be inlined. Yeah, and empty will be inlined here, and first and rest, these will all be inlined. So that means we're going to call list because we use list in our inline function. Let's just take a look at what our var is. So we're going to have, what do we have inside of our deferred CPP function? We have a var right here. So can we just do a var? Yes. So can we do a var toString? Hopefully. Yes. Okay. So here's list. We're expecting this to be needed. So I'm going to... Fascinating. So what we just did was we just printed all of the JIT compiled functions, but this was the only deferred CPP function that we ended up realizing. So it's being JIT compiled, but it's not because it's being forced to be JIT compiled by the deferred CPP function. There's some other reason. Okay. So let's put a breakpoint in our function that evaluates C++ code, which is this eval string function. So I'm going to put a breakpoint. Whoops. I did not want that. I want to put a breakpoint here. And I want to run. No way. Oh, yes way. Yes way. Because we have a cached version of it right now. So when we try to compile again, then it's just going to find like, oh, this guy's already compiled. We're not going to do anything. So where are we here? Yes, we are about to compile some code. What is our code? This is Clojure core fun 22. Which does some opaque shit, gets a symbol, gets a var, derefs the var, calls it. Okay. Not too concerned about that. And so that was one of them. And then we're here. So let's disable this one because we know this is going to be for list. We could verify that here, but yeah, we see it. So let's continue. And so here's list. We're JIT compiling list, and we're expecting that. This should be the same thing. Yes. Okay, so there's list JIT compiled. But now I'm going to disable 4.1. So we can see here that this is 4.1 because when I created breakpoint 4, it triggered in two places, right here and right here. So I'll disable 4.1, but we'll still have 4.2, which is this one, just because 4.1 always calls into 4.2. So let's just take a look at what S is here. Yeah, so this is another function that we're JIT compiling right now. Let's take a look at Y. So let's start from here because we're analyzing a call, and then we have this O, which we're going to be able to inspect. So, oh, this is our inline. So O is this first O. So first O. Yeah, so we're right, we're in F first, and we're inlining first. And so in order to inline, oh shit. Oh shit. Okay, figured it out. Okay, so this is it's my own. I mean, it's all my own fault. I guess it's all my code anyway. But in a previous stream, when we implemented the inlining of var calls, I had an issue where I said, oh, well, we need to represent the meta. Let me jump to, yeah. So something like seek. we call Jink runtime seek, right? And so we have this inline function that's actually a function object here. And then we return this list runtime seek. And then we have this problem in Jank where metadata is not currently evaluated. So we read it into data. And so we would just have a list here where FN star is a symbol and this is a vector with a symbol in there, but we're not actually evaluating it. And so I hacked that in, and I have a to-do saying once we're evaluating meta, we can remove this eval. And I just put in an eval. And so what we do is we grab our function right here out of this inline, and we evaluate it. And we do that every call. We do that every time. And so this is not linear growth. Yeah, this is going to be, so that means that like every single time we call seek, we're like anywhere in the rest of this file, and you know, in Clojure core, that's 7.5 thousand lines. All of these inline functions I added, every single time they get inlined, we're recompiling the inline function because we're reevaluating the data for that function into a new function object, and then we're calling that function object. And we're not caching that anywhere. I suppose one thing we could do is we could just like update the meta for that var, but maybe we should actually just implement proper meta eval. And then we don't need to have this hack, and then meta would be evaluated once, and then that's that. But that's the problem. And so that's why it's taking so long to compile all of this. It's not that there's more metadata that's the problem, because we saw already when we were comparing the output that even the no meta version had metadata, had source metadata. The problem here is the JIT compilation, and it's not the JIT compilation of these functions that we're defining, which is what I thought it was, which is why I was looking at the deferred TPP function, like, oh, is that being triggered? No. It's the JIT compilation of all of the inline functions. Every single time we try to fucking inline, we recompile that function. And so we end up, what do you know, like fucking JIT compiling a lot of these. A lot. Yeah, so when we take a look at meta.cpp, we can see that, yes, see, I didn't even catch this before. You'll notice that all of these functions here are like Clojure core empty Q mark, Clojure core empty without the Q mark. And, oh, this one doesn't actually have a name. Oh, this is the inline one, probably, that's why. And then Clojure core list. Wait, this is sequence length. What is sequence length? That should be count. Count. Oh, no, that one doesn't have a name just because we don't have the fucking name for that function there. And we should. And then Clojure core boolean, Clojure core int. What I'm getting at here is that all of these have the names of the vars that these functions have. But if we look at all these JIT compiled functions that were happening before the namespace, we had 617 lines of all of these before the namespace. All of these are just Clojure core fun, 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 right? And that's because 617, I remember that, 67 for all you Zoomers. So that's because these were unnamed functions, and they were unnamed functions because these are all the fucking inline functions. Valeria, welcome to the stream. I hope you're doing great. Okay. That was a journey, but we figured that out. We have figured that out. So now we have to fix it. I think what does it take to just eval meta? We have to do it during parse. We have to do it during code gen. Hey, doing good? That's great. That's great. Glad to hear it. Glad to have you. Yeah, I think that we should just solve this properly by going into the parser. And we're going to have meta source to meta. I don't actually remember how it's been a long time since I've been in the parser. Because the parser works, you know? So meta hint. We read this and then okay, and then we visit the actual meta object itself. So if it's a keyword, then we create a map for that keyword as true. And if it's a symbol, then what are we doing? We're creating an empty map. Oh, I think this just allows us to be able to parse Clojure code that has type hints, but we don't actually use it right now. And then if it's a map-like thing, then we just use it directly. Okay. And then we read in the value and we check that that thing is metadatable. And then we merge the metadata into that. Yeah, word. So I think all we need to do is probably evaluate our metadata right here. Assuming it's not an error, right here, we'll just evaluate our meta. And then when we go to merge, no, not right here, right here. Yeah. After we've canonicalized it into a map, then we'll evaluate it, then we'll do this, then we'll merge it, and that will work for parse. And then we just need to do the same thing for code gen. So let me step away for a quick restroom break, and then I'll hack this together, and then hopefully all of our compilation performance woes go away, and we can actually take a look at the benchmark benefits of inlining all of these functions. I hope it's a good one. BRB. Let's evaluate this right here, I think. So we have our meta result, and our meta result is this object source info. What is an object source info? Object source info is an object with source, well, an object with tokens. Okay. So we should just be able to say meta oh yeah, boost math tools meta programming. That's what I wanted. Expect okay. I'm just gonna pull this out now. What do we? The only thing we do with this is use the, yeah, putter. And putter was the object. Yeah, so let's just, I'm just gonna call this meta. And we have a putter. Okay, so, to mean to call, do we have something called meta? No, just unused variable. Okay. Just LSP being slow. So here we're just going to, I'm just going to use meta. And then here we're going to runtime eval. No, what's it called? It's in runtime context eval. And that takes an object. That's it for the parser, I think. And then the only other thing is in CodeGen. So when we were taking a look at the CodeGen that we had, we have all this metadata here. And right now we're just calling jank read to parse that. But what we actually want is CodeGen API. What we're gonna want is something like jank eval stir. This API that starts with all underscores is just used for the C++ code gen, because doing things like creating bars and creating functions and everything, like we're trying to keep the code gen small and also trying to keep like template instantiations and everything like that out of it. And so it's not quite our C API. It is our C++ API, so we have like full type information for the stuff that's being returned, but it's lighter. It's a lighter load than the like actually using the full C++ API in order to intern keywords and stuff like that. So if we change our read to eval stir, because I don't think we're using read for anything else, then we'll do a read string, and then we'll do right after that, then we'll do an eval. That's that. And now we just go here and we go to jank read and eval stir and eval stir, and that's it. Just those. Save everything. And then, oh, we're not even compiling. We've got almost 2 hours in and we haven't compiled anything yet. Let's compile something. Nice. I'm relieved. I was worried that this would have more sinister roots, but it's actually just a fuck up on my part. And then this means that we can remove this whole thing. I gotta make sure that that gets compiled in. All right. Hey, Papa C Dev, do you use Claude Code sometime? Occasionally, but I use LLMs more for like answering questions, like exploring designs, and not so much actually just generating code. Also, I'm gonna quiet that Slack tab. Sorry. Okay, now we have invalid call to this list. So naturally, we're trying to call the value here, and we can see that this is for transient. But this should have been evaluated. Why wasn't it? I don't know. Let's take a look at our smaller example first. So let me compile this guy. I don't actually need GDB for that. Yes, now things make sense. So we're going to start evaluating. I was wondering why this worked when I was originally writing this. And that's why earlier in the stream, when I was like, oh yeah, we can't use, we can't put inline for list. And I was thinking like, oh, we can't put inline for list because list doesn't exist yet. I guess we still could. We just wouldn't use list. We would use the interop. Why not use the interop anyway? Oh, because the interop takes a seek. It doesn't, yes. Can't do that because the interop, because the native function takes a seek. Okay, so what we'll do is we'll put list first, like so. And then we'll try this. Okay. So let me clear this and then T meta CPP. And then open up this guy. So we end up compiling this function. Yeah, we're going to end up compiling a bunch of, okay, so first off, it was 617, now it's 231. So we're compiling far fewer inline functions, and that is probably because we're not doing duplicates. We're not doing duplicates. So yes, we do need to end up JIT compiling a lot more. So that means that this inlining does come at like a noticeable compile time performance cost, but presumably it should have a very big runtime performance win, presumably. Okay, now in the case of Clojure core, I'm going to open it up over here. So we can't use list in these cases because list hasn't been defined yet. So we need to define list first. Firsty first. Where is list? List is... No way, we've already... Oh, here it is. Okay. All this is going to go up here. List is basically all we need for the inlining. Because we just use list. List. Yeah, the other thing is for this, I'm just going to use is nil on O, and that's it. Is nil on X. That's that. Okay. Now we have this issue with the transient still. Let's take a look to see, we were in this one. Let's see if this is any different for some reason. We have inline, fun, O, list. No? Seems. The difference here, I know what the difference is. The difference is the syntax. So we were using the meta hint syntax before for the others, and now at this point in Clojure core we have defen, and so we're actually specifying our map like so, instead of as a hint like so, or I guess those don't have inline, but this does here. So this is a hint on the symbol, and we end up like that works just as well. But for defen, we end up doing it differently because you're able to have a doc string and the attribute map, I believe. I looked this up, and that's what the doc said. Yeah, doc string attribute map. Although I didn't actually find an example of both of those existing. The spec here didn't seem to have it be an issue. So is this a problem with defen? Does defen need to... Presumably M is meta? Yeah, M is meta. So if we have a string, if we have a map, interesting. There's some inlining stuff here as well. I don't actually know what this is doing. But there is no eval on this meta. So where does this factor in? If we open up a Clojure REPL and we do a defen foo What was our syntax? Transient. Yeah. And then so we have meow, and then so meta on the var should give me the doc meow and cat true. Yeah, so that works fine. Now here's the question. If this is a fun that returns true, then yeah, this, okay. When does this get evaluated? Does that just get evaluated when it's being read? Valeria, is meta like a debug print? No. Metadata in Clojure is it's additional data that you can attach to certain objects, and we use it to store source information, and we use it to store we use it to store documentation. We use it to store other just sort of data that you want to tag on to certain objects. And the meta function like this just takes in an object and gives you back the metadata for that object. Not all objects can store meta. So if you do like meta on 5, for example, you're just going to get back nil. There's nothing there. If you do meta on a keyword, you're going to get back nil. Never used Clojure before? No problem. So this is being, this is probably just being evaluated when it's read. Why are we not doing that? Just hacking in the code there for the Jenk REPL so I can run it without a working Clojure core. So much of Clojure and Jenk just assume that Clojure core is loadable or even is loaded. But when we're having problems like this, we don't have a working Clojure core. So you just gotta remove some of those assumptions. All right, now generating that's going to fail. That's expected. Okay, yeah, so we can't do this either. That's fine. Okay, so now we should be able to get in. So if I want to take this guy and, oh right, I don't have deafen. All right, never mind, we'll do this. All right, I can't use deafen. Okay,
never mind. What we're going to do is we're going to keep Clojure core, but we're going to comment a bunch of it out. So we won't have the NS macro. We won't have a bunch of the module loading stuff like require and whatnot. But we're going to have defen. Yeah, so we'll get phase 1 done, and then precompiled header, and then we should actually just be able to compile Clojure core, which is right here. The reader tag, this reader tag is not supported. This is a terrible message. What is this? Huh. Huh. Okay. I don't know what that is, but I'm not gonna mess with it right now. So we're gonna do this with I'm gonna make my own defen, and it's gonna be a macro, but we're gonna define it the old-fashioned way. So macros take form and env as implicit params, and then they take a name and then args, but let's just say it takes name and yeah, no, we'll do args. And let's say that we end up just returning does this matter? Yeah, let's simplify it. So let's give me fun with name and an empty vector and meta. And then all I need is a list. And we have list right here. And I don't care about the meta on that. That is a stripped down doc string for def must be right. This is a fun, and this should grab that, and I'm gonna bring this down here. I'm also gonna propagate the name over there. Okay, so that all works. And then we're gonna do defen foo bar So it's evaluated here. As it should be. Why is it not evaluated in our Clojure core case? Why is it not evaluated right here? What's the difference? Defin is doing something definitely weird. Our M ends up being a with meta. Okay. So we don't actually compile the meta in because this is evaluated immediately. So the generated code actually just has a symbol. So that means that if we have something that is metadatable, when does that need to be analyzed? Or when does that need to be evaluated? During analysis? How do they avoid duplicate evaluation? So what sort of expert do we want? We want like a symbol. Is there a symbol expert? No. There's a constant expert. Meta eval. What is meta? Also just an expression. So that means that in eval, for primitive literals, and maps. No, not primitive literals, but maps and vectors and lists. Not lists. Not lists, but maps and vectors. And sets. We need to eval the result. Is that right? I think so. So let me that's really not much better, is it? I was trying to save on some typing there, but ends up being just as long. So yeah, what if I just do an eval on that? I kind of want to see, they must have like a map expert. Yeah, okay, where's map expert? Right here. So eval, you eval all the keys, and then you do an RT map. RT map. Create with check. See, this is just creating a map. That's not actually eval. But it's because we eval all the keys. Yeah, we're doing eval on all of the values here. So if we have a function object in there, I don't actually know the right place to put this. I think it's still in the parser. Because when we do our defen here and we have a with meta on this, M is already expected to have been evaluated. If that has a function object in there, it's already expected to be a function object in there at this point. It's got to be. It's got to be the case. Hey, Kuvi. Kuvi, man. I appreciate the raid. I hope you had a lovely stream. How's the language going? Or were you doing something else today? What were you up to? Welcome, everyone. Lonnie, welcome to the stream. Gordienko Dev, welcome to the stream. Hope you guys are doing great. Kuvi, you're the man. The timing of our streams never seems to work out for me to give you a rate as well, but I do appreciate you. You're trying to compile delimited continuations. Oh. I like your mini. You got like a proper compiler, and then you got a mini compiler. I'm just waiting. Like, is the next step a micro compiler, and then a nano compiler, and then, I mean, how small are we gonna go? What's the plan? Do we have continuations in Django? No, we do not. I think that. Microcast is going to be the same. So somebody made a library. Somebody vibe coded a concurrency library that they wanted to get merged into Django, and they're like, this, like, and then they're doing benchmarks and like, this is competitive with the Go runtime and Clojure async and Boost ASIO and blah blah blah, and that's cool. But like, I'm just like, I mean, it's not even old enough to not shit all over itself, it's infantile. I think that if Django were to get any sort of continuation support, it would be through a Clojure library called Core Async, which is like a library implementation of Go routines and channels. And there's no reason that we can't support that. But Clojure itself doesn't have any sort of first-class language support for that type of concurrency. I don't know if that's a good thing or a bad thing, Kuvi. I don't know. I'm not sure. I do know that I think this is an area that people have gone really deep in, and is not an area I've gone super deep in. Like, I will say that the best sort of concurrency experience I've had is probably like Unity's coroutines. And I think that people who use languages that have much better like first-class implementations of these things would probably like wince at me saying that. But actually, I've done like, I shipped a server in async Rust. And I guess that was just so easy. Although, I mean, a lot of people shit on async Rust. That was so easy that I forgot about it because it was just entirely out of the way. But yeah, like Unity's coroutines in C# were also like, they were really easy to just get shit done. C++ 20, I think, came out with a coroutine implementation. And so you have like their new keywords for like co-yield and co-return, but like they didn't actually provide a full implementation. All they did was like provide the framework for you to build your own coroutine engine in C++ with some keywords. And so basically nobody uses it. I think that newer versions are actually building upon that more. So maybe we'll end up getting something in Jank via the new C++ stuff, but we'll have to see. But anyway, I don't want to ramble too much on that and hold you here, Kuvi. Like you are most welcome to fly if you're exhausted at the end of your own stream. I know how that goes. I appreciate you either way. Rust and C++ is stackless coroutines. Okay, I will readily admit my my ignorance in this space. So you prefer stackful coroutines as a user? Okay, so are you Nadia? Welcome to the stream. I appreciate you. Hope you're doing great. So stackless versus stackful, is this the implication that you actually just have like a, like an OS stack that you have some stack variables on, and that stack is sort of swapped out as you switch different evaluation contexts? And like, if so, like, how would you even do stackless? How would you have local state and not have something be stackless? I guess I don't know enough of the details of how these things are implemented. Or do you not get local state for the stackless ones? I swear in Rust's async that I used, you have local state. I don't know. I don't remember. Got to do a deep dive into concurrency myself for my line. Yeah, this is not an area I'm strong in. And it's not like, professionally, it's not like as a user, it's not an area that I've had to do much in. Like, I've used Core Async in production for Clojure. I've shipped an async Rust server using Rocket. Is that what it was called? Rust Rocket Launcher. Oh, this is going to be the Rust game thing. I don't even remember. Web framework, maybe. Stackless is basically converting code into a state machine. Okay, yeah, and that's kind of like your stack is encoded as a type. Okay. So sort of state machine based coroutines are kind of like the quintessential, the like classic coroutine implementation, where you have some macros that use like source information in order to create a stack machine, or in order to create a state machine that can simulate like concurrency, or at least that can simulate a language that has first class concurrency. But the stack full actually uses is actually first class and has an OS stack that it's, or at least it's probably not an OS stack, but has some like virtual stack that it's actually swapping out. Is that right? Not at all putting you on the spot to school me for all this, but schooling is indeed welcome. Yeah, server stack like threads. Yeah. Okay. Yeah, so the JVM, this is a big deal in the Clojure land, because the JVM just recently got like green threads. And so then everyone's like, "Oh, can we get like a version of Core Async that's implemented using these green threads?" Because I think it was like previously everything was tied to hardware threads, and then there were allegedly some big performance wins to get out of that. Yeah, in the C++ space, we have such a lack of richness when it comes to these sorts of runtime options. I feel like people in other languages, like you're using OCaml, if I'm not mistaken. The C++. I think that's got to be a social thing, like a cultural thing. C++ folks are just for as quickly as people complain the C++ language is evolving. It is also just so antiquated and backward in its own way. Hey, Grap, maybe. Oh, hey, kept me signed in. That's convenient. As long as you don't have your tinfoil hat on. What were we? We were doing parsing, evaluating metadata, parsing maps. We're implementing optimizations of things. We're currently optimizing a ray tracer in Jank, the native Clojure dialect, in order to compete with Clojure JVM. And so this is one output of the ray tracer. It does generate random scenes, but they all look basically the same because the only randomness is that these little spheres are in different positions and have different colors. But it's basically this. And so we were optimizing the inlining of calls in our compiler, and then that led us to go down a whole rabbit hole of technical debt, where I had hacked in some inlining stuff, and then that exploded the compile times, and now we're trying to do that. We're trying to do that better. Software rendering, yes. So this is meant to be a benchmark of the Clojure compiler and runtime. So we're not doing, we're not actually trying to be fast. We're not trying to write a fast ray tracer. We're trying to take a ray tracer written in Clojure, software ray tracer written in Clojure, and make Jank as fast or faster than Clojure JVM is. And so, one is like the ray tracer itself is not written to be fast. It doesn't have type hints. It has a lot of like polymorphic arithmetic, boxed arithmetic. And that's the one thing. The second thing is we're not allowed to change the code, because the whole point is we take the same exact code, we run it in Clojure, we benchmark it, we see how fast Clojure is, and then we run it in Jank. We see how fast Jank is. So we just did this in the last few weeks. We were doing this with Fibonacci, again, like a recursive, super naive implementation with a lot of boxed polymorphic arithmetic for Fibonacci. And so that was a benchmark that we were focusing on. We got to the point where we were 40 times slower than Clojure when we started, and we were almost twice as fast as Clojure when we were done optimizing that benchmark. For this one, I think we started out, this was 49. So Clojure is at about 22. I need to update these. But so we were about twice as slow as Clojure, and now we're about 50% slower, based on the last update. Still working on more changes though. I haven't been able to focus on optimizing Jank much the past couple of years, because I've just been focusing on parity with Clojure and seamless C++ interop and all of these fancy things that Jenk has. We're finally at a point now where I get to focus on optimization. So I'm just doing that every stream and then putting out blog posts on the, like, I'll pick one benchmark, focus on that for like a couple of weeks, put out a blog post showing, the progress, pick up another benchmark. And we have this, I don't know if I can actually search for it. Is Jank fast yet? Let's see if this shows up. Hey. So we have this, wait, this is the actual thing. We have this dashboard now where we're showing Jank's performance. And so I love this one because this is the Fibonacci that we were working on, right? And so this latest drop, right, to get below the blue line, and the blue line is Clojure, that was our latest effort in order to get Jank from being 6 times slower to now almost twice as fast as Clojure. And so we still need to tackle like this benchmark because we're way up here, Clojure's way down here. And then we're currently working on this one. And so you can see yesterday I merged in our first step toward getting faster than Clojure, and that is this huge dive down that we have. Well, you guys don't get to see that because my fucking head's in the way. There we go. Is that updated? Yeah. There. So we have this huge plummet for Jank, and we're this green line. We're trying to approach this blue line, and we're still working on it. Nadia says, I have no idea how well my Frankenstein thing can cope with concurrency and parallelism. I have doubts verification stuff can keep the AI stuff from introducing bugs right and left in it. Zircon is heavy C++ and OOP methodology and is close to the only place I've seen it in 20 years. Zircon. Why does this... So this sounds familiar, not the mineral, but fuchsia. Zircon is the kernel that Google's working on? No, Zircon is a formal verification tool. But fuchsia is the Google... Fuchsia's the Google thing. Fuchsia's Fuchsia's the kernel, right? I gotta remember all these things. Formal verification in C++. That's fascinating. That's a whole area that I don't know much about as well. Zircon is the C++ kernel separate from compilers. What are your thoughts on verification versus something like FIL-C versus like effort required and I guess like basically in terms of return on investment is what I want to say. Effort put in and value taken out. Okay, there's no specific language attached. It's attached to language descriptions are part of its input. That's super cool, Nadia. Hats off. Keep at it. You and Kuvi. Okay, wait, speaking of stacks, I gotta pop the stack back to where my brain was here. When we parse a map, we need to eval the map. This guy right here. And so if we want to see this in the Clojure code, this would be inside of Lisp reader. Do we have eval reader? No. Is it just kind of all over, or are there big places where Jank can get performance wins over Clojure, like vars and data structures that the JVM doesn't natively understand? Well, so Jank is on the LLVM, and LLVM also, doesn't understand things like vars and whatnot. So one of the things that we did recently was we added, so Jank compiles to C++, and the reason that we do that is that Jank has C++ interop. Jank has like seamless C++ interop. So like better C++ interop than you're going to see anywhere. And an example of that is, I think a pretty good example of that is here. So this is like at the top of a Clojure file, you normally create a namespace and you say, okay, so my namespace is called, I guess this should be called like my app or whatever. And then as part of that, you can just include some C++ header file, like a boost file system. And then you can grab a symbol like boost file system file size, which is a function. It's actually multiple functions because it's overloaded. And you can just rename that symbol to file size. And then later on, you're entering some like dynamically typed polymorphic Clojure code, but you have this call to file size. And so we do overload resolution here and everything like this. And then print line is like we're back into dynamically typed land, but then this stuff that can throw, and then we can catch like boost file system errors. And so E is, we can call virtual, member functions on that as well, but then back into dynamically typed land. And so trying to do this seamless interop where we go back and forth between statically typed C++ and dynamically typed Clojure, it just makes sense to compile to C++. If we were to compile to LLVMIR, which we have done, we basically need to implement C++ compiler shenanigans and like ABI stuff as well as optimization stuff ourselves, which sucks. And so we used to compile to CPP, and then we went to LLVMIR, and then we went back to CPP, and because it just like compiling to LLVMIR just didn't make sense. There's so much that we need to do with C++, that we would basically be re-implementing a C++ compiler. Like we'd be re-implementing Clang at that point. And so LLVM ends up working in the case of LLVMIR, like Clang takes all the C++ that we have, compiles it to LLVMIR. LLVM works with the IR. But at that point, like the notion of vars and immutable data structures and everything like that is gone. And so we added our own IR implementation that's much higher level. And we have a reference for it here. But so Jank has its own SSA-based IR, and this works at the level of Clojure semantics. And so we have instructions for things like var derefs and dynamic calls and whatnot. And so this allows us to perform optimizations at the level of Clojure semantics before we get to code gen. Higher level than MLIR. This is So my understanding about MLIR is that MLIR is kind of what you make it. And so I think that MLIR could have been used for this. But when I was chatting with Clang and LOVM devs about making my own IR and asking about MLIR, nobody really had a great impression that MLIR was like a solid choice compared to using my own. So what I can say is like Jenks IR is very specific to the way that Clojure works. And it is like not general, it's not generic at all. It is custom tailored to the way, to describing the semantics of Clojure programs. And that's exactly what we want. Like, I'm not trying to build like the JVM. I'm not trying to build like a general virtual machine. I'm specifically just trying to encode the semantics that we have in Clojure, so that way in SSA form, so that way I can optimize them. So my understanding is that MLIR could have been used. I chose not to use it. And the Clang and LOVM devs I spoke with seemed to bless that decision. Form of verification has got a lot of mileage debugging because break. They're difficult to spot by hand. I just found such a race earlier tonight. You're not trying to build Frankenstein too. Oh, what do you mean, Nadia? What do you mean? Map reader. RT map. I don't know where the eval actually happens here. You trying to build Frankenstein, or are you trying to build Frankenstein's monster? I think that, I mean, Jenk is definitely Frankensteinian in the sense that, like, it's the only programming language in the world that is both a Clojure dialect and a C++ dialect. And so it has like all of the pros and cons of both Clojure and C++, for better or worse. That's quite Frankensteinian. Frankensteinian. We can eval here. I just don't know if it's the right move, but let's do it. Oop. So if we do that here and here, unable to resolve symbol and because no, not here. These are quoted. That shouldn't be a problem. Also, like, unfortunately, no idea what's going on with the error output here. Lovely indication at exactly where the problem is. More work to do there. But what's the deal? We got ands. Yeah. I think, it's got to be all those semicolons, right? All those semicolons are on line 1 because that's right above the copyright notice. There are some inline functions that have and. But we don't have any of them here. One option is to bisect. Frankenstein's monster was made from the parts of numerous cadavers. So I took the front ends off 23 language compilers and glued them all together with MLIR, LLVM, and Coca's effect model. Damn. See, now that's helpful. But why? This is quoted. There's a subtlety here. There's a subtlety here that I'm missing. Mm-hmm. Yeah. There's a subtlety here that I'm missing, and I don't know where this eval should go. I think the problem here is that we're double evaling, which is why we eval this once, and then we try to eval it again, and then that's why we end up trying to resolve X here. So one thing we can do is we could just work around this for now. So if we start with our transients, if we were to if we were to take this guy, I believe, and then we tag that there. No, it's still, the meta still here is not, okay, because that's for transient. And I did that for transient. Okay. Whew. That was about to really blow my brain. Yes. Okay. This works. And now I don't understand the fucking difference. Right now, like, I am owning this. The difference is not fucking clear to me. Mm-hmm. But I am going to work around it because we know this works. We know this approach works. Let's do this approach. And then separately, I will ask around, and I will find out where that eval is happening for the other case. But it doesn't matter to me if this is defined before the symbol or after the symbol. I just did it after because it was easier to copy and paste. Those are all before. And this. And so we'll end up with a to do. I do TDD, which is to do driven development. How many of these do we have? Oh shit, we have 30 more. Okay. Can we macroize this? Let's see. Take this line, match it here, yoink this, go up 2, drop this down, go up 1, paste, do this, jump 2. Let's see. Yeah, that was fine. That's fine. Oh, that one didn't work. Why not? Up 2. Oh, because we went up 2 and then we have to go over. We have to make our macro smarter. Okay. Wait, these don't need the macro anyway. All right, let's try macro again. So grab this, match. I want to go, oh shit. No, because this has a longer doc string. So we have to be even smarter. Okay. I can't go down 1. I have to match. And then we'll go back to deafen. And then we'll go forward 1. And then we'll drop this down. And then we'll paste. And then we'll do this. And then we'll search. But it's going to search deafen again. That works. That works. That works. Does this save us time after all? Probably not. But was it more fun? Yeah. So that was a 2-line doc string. Did that work? Yes, it did. Nice. Yeah, that looks good. This is a 3-line one. Does that work? Yup. Okay, I'm pretty confident in this now. Oh, that's a chunky boy. Does that work? Yup. All right, we only got one more. Okay. Bit shift left. Oh, what did I fuck up? Bit shift left. Where did bit shift left go? Oh, where did it go? I swear those macros were looking fine. Oh, it's it shift. I don't know why those didn't work. I don't know why. That's a good error though. See, we do get some good errors. We better. Put a lot of work into that error reporter. Also, I completely missed. I don't know if you're still here, Papa C Dev, but I appreciate the 20 bits. You were the very first person to throw out bits, and so I didn't even know what to look for, but I see it now. I see you, and I appreciate you. Okay, so while that is cooking, what is this guy? I've never seen this before in my life. Have I done something bad? Like, those are all hacky, that's fine, but is there like, did I do something weird? So I moved that up. This was just changed, that's fine. This is fine. Fine. I'm not seeing any weird reader stuff. This one uses syntax quoting, but that should be fine. Like this implies reader tag is not supported. What is the, you know what, reader tag is this blah, blah, blah reader tag is not supported. Util format. I'm going to print out whatever the fuck this thing is. Here. And then sim. Yeah. Meanwhile, scanning. Wait, that's everything. Yeah. This is totes fine. Totes my goats. It's totes fine. This object reader tag. Oh, fuck. Okay. Yeah. So that is because we have an object being like, it's doing something like this, and then it's doing something like this. And that's because we've actually read, that's because we've brought a function into a map, and then where is that getting printed though? Yeah, let's take a look at, I think we'll do Jank phase 1, compile module, Clojure core, and we'll do a GDB on that, and then we'll want to break in this guy, 1067. Nope, that's not right. Right here, 1043. Wait, why didn't that break? Wait, that's not the one. Where? This is the 1091. That's what I said. Yeah, 1091. Try again. Yeah. Okay. So we're reading. So what is this string that we're reading here? Yes. This is the problem. I don't know how Clojure handles this. So the idea is this. You have a function like this that has some metadata on it, that has a function in there. And when you AOT compile, you need to end up, so like part of AOT compiling in Clojure is JIT compiling. And so you need to actually evaluate this function into a function object. But when you AOT compile, you need to write out this metadata in a way that actually still has the function source here. So that way your AOT compiled code, when it loads up, can then eval the function from source again. And so that means that you can't just take the metadata, evaluate it, and then have that be your metadata. And then when you write out your metadata to AOT, to your AOT compiled code, you just take the metadata that you have in your var right there and write it out to a string. Because if you just try to write that out to a string, like we just did, when you try to write a function out to a string, you just get this object. You just get this object syntax. Clojure doesn't have a way to just say like, oh, okay, well, yeah, just give me the source of this function. That's not something that Clojure does. And so there's this duality where for the runtime, we evaluate this function, but then when we write this back out to AOT land, we somehow go back to the original data. Yeah, so there are two areas that perplex me when it comes to Clojure. When it comes to Clojure metadata. And so that is when is the eval done? And we're talking about Clojure JVM for something like this. Oh, that's exactly what I wanted. So we'll have something like we don't even need this. So that's the first question. And then the second question is, how do you write how is original meta kept to be written out for AOT? Question marks. And this is such that we get fun instead of object. Yeah, I wonder if yes, Matt, Clojure has two quoting mechanisms. There's syntax quoting and then there's normal quoting. So you can see normal quoting right here. And then syntax quoting allows, it does automatic namespacing and allows for splicing and escaping. Whereas normal quoting just is wholesale, very simple. Yes. Yes. That is, I think, Matt, what is happening. But then, yeah, just carries a lot of weight, because then you have the question of like, okay, so where is that being stored? It could be that the var in Clojure. So let's say that we jump back into here. And we did something like this. So we have this meta, and then we grab the var itself. We'll see that we have the doc for meow, which comes from here. And then we also have cat as a function object. And here's that pound object syntax that comes from this function right here. And so this implies that like meta for the var has the function object. It has the evaluated meta. But during AOT compilation, this data must be available somewhere else. Like the unevaluated, just pure data form must be available somewhere else. And I don't know where that would be. Because if you do this, you do the var deref. That's going to be on the function object. That's going to be on the function object itself. Because the type of foo is this function object. That's honestly not very helpful. But you can say function, yes, true. But the meta on that is empty. And the meta on the var, what about the meta on the meta? Like, are they getting super meta with this? No. I was wondering if maybe the meta on the meta was the original meta. I mean, that kind of makes sense though, right? Because maps support meta. So there's nothing saying we can't do that. But that would mean that like if you want to get the true meta for something, you need to like follow the tree of metas all the way up to the until the meta of your current meta is nil. So I mean that is a way we could do this, but Clojure is doing it a different way. What's the meta of that object? Okay, so let's do meta, and then we'll get the object, which was cat, and then we'll grab the meta of that, nil. Oh, you're all good, man. Don't worry about it, man. Yeah, you're all good. Yeah, but the meta on that's nil. And so I see what you're saying there. We're like, oh, well, maybe the function object itself had meta on it. That was its source or something like that. But it doesn't. Yeah. I think that there's a good question for Jank in that, like, in this case, the map here is not evaluated. So that way we don't have a function object being true. But why is that? When we parse it, we don't evaluate it. We evaluate it when we go to eval. And we never go to eval because the macro for defen, which we don't have open anymore. We could open it here because it's the same for Clojure. The macro for defen just does a with meta on the symbol. And that's where our meta goes. And so the generated code just ends up being like a def and then foo and then some fun. And foo is a symbol that already carries that meta. And so it never gets evaluated. Does with metadata evaluate it? Just calls with meta on the object. So I don't think so. Yeah, so with meta here just creates a new map with the meta. So I've still not found where this happens, where the eval happens in this case. And it doesn't happen. Here we check for inline. Ooh. Wait. What's going on here? Is this the hack? We check if there's an inline variable or an inline value inside of the meta. Then, oh, fuck. We're doing first and second on inline, which means that we're expecting it to not be evaluated yet. So that's a hint. Defen is not expecting this to have been evaluated. And so we're expecting to pull out fun as the first, because inline here should be something like fun foo and this sort of thing. And so we check the first of inline is this I fun, and then second in line is this I name. And so what we say is all we're doing here is we're inserting a name. Is where we're saying if iPhone is equal to fun and iname is not a symbol, then inserts the same function name to the inline fun if it does not have one. Got it. So that must mean that this gets evaluated later. When? Where does this inlining happen? Let's find that. Is inline. We're gonna start at the top. Inline key. Inline arities key. Where are these used? So if we have a symbol or a var, we look up the var. If we have a var, current namespace, we get the meta inline key. We check the inline arities. If it's null, curious, this is a predicate called isInline, but it actually returns the function. So it's serving double duty. So let's look at where isInline is used. We have two references to it. That's going to be the definition and then a single usage. So if we have an inline function, preserve tag. So we take inline, we apply to, but why is inline a function here? Hold on. Okay, so when we get the inline key out of the metadata here, we're already expecting it to be a function. But in defin, right here, we're not. And so that means that it must be turned into a function. Inline key is only used in these two places. So if we go to our def expr, also, the indentation of the Clojure code is just inspiring. Yeah, it's not happening when we do the def. When we eval the def, we're not includes explicit metadata. This is commented out here, commented out. So this is not actually used. This is just code that's commented out. Nice. so it's still not clear. We have our def here. Our symbol has meta that has a function as data, not yet evaluated. But by the time we pull the meta out of the var, so this is v is a var, look up var, the inline key is expected, or the value of the inline key is expected to be a function. But in the def exper, which is where we set the meta on the var, right here is where we set the meta. All we do is we just do an eval on this meta expression. Meta is just an exper, and we just do an eval on that. So keyword exper, import exper, host exper. I'm gonna jump. Qualified method exper. We're done with expers apparently for a while. Instance field exper, static field exper, phi support, method exper, instance exper. Can I just do a something like this, 18 expers, maybe primitive exper, field exper, constant exper, this doesn't have an eval. Probably comes from literal exper. Where is literal exper? Abstract class. Eval just returns val. And then there is a map exper. Eval calls eval on all the values, and then just calls runtime map. And I already took a look at this. Runtime map right here just creates a map. Doesn't evaluate the keys. Hash map create with check. Yeah, we're just creating objects and putting them together. I don't know, man. I might need to ask on Slack, the Clojure dev channel. Because somewhere in between right here and that is inline check, clearly this metadata, or at least the function and the function behind this inline key, gets turned from data into a function. But then that somehow survives, that data somehow survives through to AOT compilation. So that way when we write out all the data, we end up writing out the original. I don't know. Yeah. Well, I'll call that a dead end for now. And I don't really feel like picking up something else. So I think I'll wrap up. Yeah. There are some things in the Clojure compiler that are just like, there are some things that are just really obvious, and then there are some things that are just like, what the fuck? And then they're very delicately balanced as well, you know? Like, if you slightly change the way that these things get put together, then it doesn't quite work. Does not quite work. Got no one else I want to send you guys to. So, hey Matt, congrats, man. Nice work on that fib improvement. We'll have to maybe we can get some dashboard that has Steel and Jank running on these benchmarks, and we can do some very friendly competition on these. Might be hard because it's we'd have to choose things that are like that port well between Steel and Clojure. I wouldn't for sure. I don't know, man. You got the power of Rust and you have a JIT compiler. Be right back. Learning the whole program. Yeah. See, like we both have full control. I don't want to. If I will win for sure, then let's not do it, because that wouldn't be fun for you. But if you're also beating Clojure, then I figure you're up there. This is gonna be like when we did the. Oh, I'm not in the right place. When we did the inlining for the Fibonacci, it was a big win. We went from 36 here to 19. So this is almost a 2x gain from inlining the arithmetic. So I was really hoping that inlining like all of these various functions that we have for the ray tracer is also going to be a really big win. But I didn't realize that it was going to be such a heavy thing. It's all good work though. It's all stuff that needs to be done that improves the robustness of Jank. But sometimes, like especially when you're like, oh, I've already inlined some stuff, you know, like, and it worked. It was like we did it on stream, wasn't bad. Let me just inline some more. Should be super easy. And then compilation times explode and you're like, what the fuck? And then and then 4 hours later, you're like, okay, okay, fair enough. I did not respect you enough, sir problem, but I do now. Anyway, I want to figure this out because that's what my job is, and I will have this. I'll have this done for you guys next time. I'll show off whatever the fuck it was, unless it was super annoying, in which case I'll say it was super annoying. But next time we're going to be jumping into some more optimization stuff as well, most likely, and we're going to get this. We're going to get these numbers down for the ray tracer. Right now we're about 50% slower than Clojure, and we're going to get there. I have no doubt about it. I hope you guys have a great week. Thanks for hanging out with me. I know this one was a bit of a churn, but that's life. That's software development, especially when you do it yourself. So have a good one. I appreciate you hanging around, and I'll see you next time.